name's Will Coon. I'm going to be talking about a IRAD this year with Brian Robinson here on actual artificial sleep for improving AI and continual learning. Next slide, please. This is a sophisticated audience, so I don't have to spend too much time. Next slide, please. Thank you. Going into what continual learning is, but for today, let's just define it as the ability to acquire new information in succession without overriding or interfering with or forgetting prior learning. This is something that neural networks really struggle with, but it's something that humans and mammals can do pretty well and fairly easily. This is in large part thanks to sleep, actually. Next slide, please. Sleep turns out to be critical for information processing. Everything with a nervous system sleeps, and as you climb higher into the phylogenetic evolutionary tree, more sophisticated nervous systems require more complex or sophisticated sleep, and you start to see more specialized sleep states that play different information processing roles and interact together, cycling over the course of a night. Next slide, please. The three pillars that I like to refer back to most often are a synaptic downscaling process. This is the brain downscaling all of its synaptic weights in the cortex proportionally, which has two principal effects. One, to lower the absolute cost metabolically to maintain that synaptic infrastructure, and it also has an effect of cranking up the SNR, not by amplifying signals so much as dropping out the noise floor, by reducing low weights, and eventually small weights just get reduced entirely to zero. Another exciting aspect of sleep is dreaming, which seems to be really important for creativity and insight, and has even been hypothesized by a group from Tufts to have evolved specifically to prevent our brains from overfitting, essentially. And the most tractable and easiest to deal with, I think, concept is the one in the middle there, memory replay, which has started to see some applications in the CL, continual learning field, with or without the couching in a narrative focused on sleep. Next slide, please. Just last week, we were privileged to hear a talk from Hava Siegelman, the middle author on this really great paper from 2020, where they showed how memory replay can benefit continual learning neural networks if they are structured in a biofidelic way. Next slide, please. So let's get our bearings on the model of our problem and the model of our model. On the left, the task, we're asking a neural network to learn a bunch of things, and those things could be alphanumerics from MNIST, or mostly today we're going to talk about learning image classes from the Cypher database. The most implausible way to implement memory replay would be to rote transcribe every example you see on some kind of hard drive, and then just reproduce in a rote manner examples to replay experience. This is clearly not how nature does it, and it's not optimal for any artificial system as well. Next slide. It's much better to maybe train an autoencoder. So on the right, we might take our inputs and then condense them to some lower dimensional, higher representation in a artificial hippocampus, so to speak. And then for replay, we just ping that generator to produce recent outputs that can be fed into our cortex. Even more biofidelic would be to merge those two, and in the next slide, we actually collapse, we remove the redundancy of having two sets of feature weights, one for the generator and one for our long-term storage. In this case, the same sets of weights are used to acquire new information, real new data inputs, and are also shared for the replay process when new examples are generated from memory, essentially, in the hippocampus there. Okay, next slide, please. So here we're looking at results from two different types of continual learning tasks. We'll start on the left. They call this a task incremental learning. And in this case, when you are evaluating performance of the model, we've taken the Cypher databases and of 100 things and divided it into 10 episodes of 10 things each. In this task incremental setup, what they do is test only within an episode at a time. what we see, without going into the specifics of all the lines, the vanilla flavor model will start to lose accuracy on the y-axis to the left as you start to add more episodes of things. And they show quite nicely in this paper that various flavors of replay, so the colored line towards the top, preserve learning as you add tasks. This is also a fairly simple task, and you'll see the performance kind of asymptotes there. A much more kind of interesting problem that's also more what reminiscent of real life is testing the model on the sum total of its experience. So in this one on the right, the class incremental learning scenario, the model is tested first on the 10 things it learned in the first episode, then on the 10 things plus the previous 10, so on and so forth until it's being quizzed on all 100 things. As you start to overburden the system, you see a drop in performance. Still well above chance, but it starts to become too much to retain. And the paper shows, again, that some various flavor of replay in this architecture can slow that drop in performance or preserve some latent information. Now, what we really like is to make that chart on the right look like the chart on the left. We want to keep performance as high as it was for the first training episode and not see this kind of gradual decline. And if we think about what's happening here, what's going on with these weights as we add tasks along, weights trained in the first episode are trained once and then exposed to 9 more successive ways of alterations, modifications, and training. So you can actually imagine them starting to erode over time and kind of be reduced to this beige mud of low caliber weights, increasing the noise level in the network. And if you look at the performance of the models, if you look at the distribution of correct answers after you've trained in all 10 episodes, it shows a preference for the most recent learning most. So if you look at all the correct answers the network has, the bulk majority of those correct answers are from the most recent task. And then the next smallest is the task before that, until you get to the first task, which it barely retains at all. And of course, this is really not what we want in a continual learning scenario. We're only really kind of like slowing the decline of something that's clearly going to fizzle out to zero if you have this thing operating ad nauseum or ad infinitum. So the brain faces this exact problem, this kind of erosion of weights, and we mentioned it very briefly at the top, the synaptic downscaling process during slow-wave deep sleep. Again, during slow-wave deep sleep, the brain subjects the cortex to these hypersynchronous oscillations, traveling slow waves that have the effect of downscaling all weights in proportion and dropping out the bottom, essentially dropping out the beige mud or the noise floor. So building on this replay work, we asked whether a model that not only replayed biopedalically, but also took advantage of synaptic downscaling might retain more information in the continual learning task. Next slide. I think we're going to skip a couple. Let's skip this one, and let's skip this one. And let's actually skip this one too. Next slide. All right, yeah. So in this model, in this graph here, we're looking at the performance of our model with various amounts of downscaling, or here it's labeled pruning. So this color is no pruning at all, that's the baseline performance, 25% or drop 50%, and those percentiles tell us that in the 25% case, for example, we are stacking up all the weights, ordering them by magnitude, and dropping out the lowest X percentile in our downscaling process. And what we show is that there is a marginal benefit in performance conferred by different amounts of pruning, and there's clearly one that seems to be more optimal compared to the rest, but this is nothing to write home about, right? It still more or less looks exactly like performance without pruning. That is until you start to look underneath the hood and look at the distribution of information that's been retained. If you go to the next slide, please. This is a different way of looking at the same data. Now we have each of those 10 episodes here. And within each of those 10 episodes, we're looking at 3 different amounts of downscaling or pruning. All that we really care about for today are the leftmost bar in these plots, which is no downscaling, no pruning, and the rightmost, which is, let's just call it an optimal amount of downscaling or pruning. And the colors correspond to the task learned. So again, we were talking about if you stack up all the correct answers the network has and ask from which task did that correct answer come, you can map that to a color and see, like we explained earlier, that there's this preference to the most recent task learned with a successive decrease as we go further back in time. So task 1 is basically barely remembered at all in the no pruning case. Compare that to the pruning case, where the distribution is much more evenly spread. And if you compare the first task here, blue, on the pruning side versus the no pruning, it is really striking how much more information is retained. This is really the effect that we want to overcome the catastrophic forgetting that we see in most continual learning scenarios. We want to make sure that the earliest learning we've encountered has not been overridden or subjected to interference. This seems to confer that benefit. We're not all the way there yet. Again, the average accuracy is nothing to write home about, but this was a surprising and really interesting finding that we're very excited to explore further. Next slide, please. Speaking of which, so this is really exciting. We've taken a replay model that kind of simulates a light, non-rapid eye movement sleep, I call it, among those 3 pillars. And we've added another sleep state, a synaptic downscaling process. Now we have 2 different information processing motifs that are modeled after the information processing that we see in mammalian sleep and confer benefits to artificial neural networks constructed in a biopedalic manner. I just can't overstate how exciting it is to see an entire blueprint where all of the information processing motifs in these circuits are very well understood in the mammalian brain at this point and ripe for the picking to translate into applications in artificial neural network construction. So we'll be very excited to move on to adding the 3rd of those 3 pillars, which is a kind of RAM or generative modeling. We expect that will prevent against overfitting, and we're not exactly sure how that will interact with the 2 sleep stages we've implemented here. But this is just to scratch the surface, and hopefully the main takeaway here is that there is a value to this blueprint sitting right in front of us, right under our noses. And we can learn a lot by taking those lessons that have been proven through evolution and time and applying them in our constructions ourselves. Last nugget to leave you with is that the benefits of these sleep processes may be even more pronounced in neuromorphic, that is, spiking architectures. So networks that operate on these, like the Loihi chip from Intel, that compute information through time-dependent spiking processes. There's been some nice work in the synaptic downscaling literature showing preservative effects in neuromorphic hardware that's really exciting as well. So stay tuned for updates. I'll open it for questions and finish there. Oh, Mike and Bart. Okay.
I wasn't sure if I was tracking when you said like when you sleep, like those lower weights kind of get dropped and the mud kind of goes away. It seems like are you only retaining then? How does that translate into what you showed where the distribution was very even with what you retained? You know, kind of at the end of those 10 classes?
Right. That's the really interesting question to ask. We haven't looked yet, but we would expect, I think, based on what we talked about, to see a lot of very strong weights that are orthogonal representation. So hopefully if we looked at the weights needed to reproduce task 1 versus task 10, they should be separate collections of sub-networks of the network. Really interesting to follow up on, Bart.
Yeah. Okay. So I think I've sort of teed up a version of this question in some discussions we've had in the past, but I don't think it was ever answered. Maybe now's a good time. You mentioned this blueprint, which I definitely agree that we have these great blueprints from biological intelligence that we want to translate into improvements for artificial intelligence. But some of those things are probably artifacts of the constraints of biological neural networks and other things that are true for biological systems that don't need to be true for artificial systems. Are there any things that you can point to, just from the work that you've done, that you think are really artifacts of biological neural networks that we really don't need to include in our blueprint for artificial sleep, or you think that it's all on the table currently?
This is the question I carry around with me every day, Mike. And the short answer is I don't think we know, which is actually, to me, really, really very exciting. We have a lot of work to do to prove out which of these are substrate-independent information processing motifs versus something that's necessitated by the specific implementation architecture, be it neuromorphic or not. Thankfully, we have jobs to pursue those questions.
So much. We're actually
Thank you.